structures. Okay, so this is session 2.
Cool.
We're going to talk about data structures in SuiteSparse.
Can you hear me okay? Is the audio okay? My
Yep.
charging.
Yeah, sounds good.
Working on my Mac microphone right now instead. So, all right. Well, I am also going to, in case I need it, I'm going to have this available. This is my I need to change it on my focus so that it holds the focus on the camera, but I haven't figured out how to do that yet. So hopefully it won't be too distracting. I've got to figure that out. Linux thing, right? I think
Yeah, right. Yeah.
is I need to do it. All right. So let me share my desktop. I think I'll spend, because since it's a data structure, I may end up drawing some things.
For sure.
Okay. So the code. Whoops. Wait a minute. What screen am I sharing?
I see 2 terminals. Side by side.
Yeah. Okay, I get it. Yeah. It just didn't show the boundary because of maybe the recording. I don't know. Okay. So I'm in the Dev 3 branch right now, GraphBLAS, which now you asked last week, all these source code changes I'm making, when will they be released? Well, it's already 9.3.0 beta. I put out a 9.3.0.beta1 in the GraphBLAS repo.
Great.
And I moved things around a little bit. I decided to leave this in place. That's not necessary for today's topic, but otherwise the source code structure is the same. And so, when you think about the matrix data structure, you would think it might be in here. Whoops. It's not actually, but these are helper. The data structure is not here, which is kind of weird. I could probably move it there. But the core operations to touch the matrix, to reallocate the matrix, to create a new matrix and query basic things about the matrix is here. Okay. Now, I also have a folder called vector, which is very terse. And I have a folder called scalar, which is a little bit more because I have a notion of a scalar wrap. This is not user callable. And and there's scalar clear here. Do I have a folder? Oh, this is, you know what? This is in the wrong place. I have a folder called clear, which this GRB scalar clear should be moved to this folder. So basic methods are here, but some other basic methods like clear the matrix, clear the vector, that's in its own folder. But the definition of what is in the matrix, what the data structure is not there. It's in the built-in folder, which I could break apart probably, but I haven't gotten that far yet. So the built-in folder includes some include files, which are really templated include files, but the folder is called include to distinguish from templates. All the include files are .h and templates are .c code. So, but I sometimes use include files in a templated manner. And so what is in the matrix? Well, a matrix is a vector is a scalar. Yes, they're all the same object internally. A scalar is just a 1-by-1 matrix, no difference. Everything you can do with a matrix, you can do with a 1-by-1 matrix and a scalar and so forth. A GRB scalar is a 1-by-1 matrix internally. And a vector is just an n-by-1 GRB matrix. And I don't provide this to the outside user, but you could, if you had a n-by-1 matrix, you can literally typecast that to a GRB vector and it would work.
What about 1 by n? Is there a distinction internally?
A 1 by n, no, that would break. That would not be a GRB vector.
Okay.
I do have a macro internally that tests, is it okay to do the typecast from a vector to, no, from a matrix that's n by 1 to a vector. And it has to be a CSV format, it has to be stored by column. My vectors internally are all imaginary by, I imagine them stored by column. And you can't change that because it doesn't really matter. If you write a vector this way, fine, I know what you're doing. If you like on
Right.
your slide, if you had a vector times a matrix, well, fine. Yeah, I know the vector is supposed to go this way because the spec actually says, if you read the spec, it literally says in the math, that's U transpose times A.
Yeah.
The
Just
row
like
vector,
MXV versus VXM. Yeah.
exactly. VXM is written as, in the spec, it says U transpose A. And so the spec doesn't define a vector being column vector. It says, oh, it's, whatever, it's amorphous. But when it does the math, it does. So I just say, fine. Vectors are supposed to be columns. Full stop. Okay. And the reason I use this funny include structure is because of kind of unfortunate thing about the generic functions in C, the underscore generic switch case on type for creating polymorphic functions needs different types, and the types can't just be type def to one another. Like I can't say here's a GRB matrix struct, and here's a GRB matrix struct, and I'll type that to a GRB vector. I would like to do that, and I could, except generic says in the switch case for generic, it says, well, I don't know what you're talking about. These are the same types. You can't do this. So I had to fool it. So let me show you my matrix then. In the code restructure, so these are built-in template operators here. This is .h, yeah. Okay, no, this is the wrong thing. Hang on. Oh, it's here, actually. These are the definitions of all my opaque objects. It says built-in include gbopaque.h, and I probably should kind of break this apart so I have the different objects defined in different files, but so far it's just I just moved files around. I didn't rename them. And these are all of my internal, like every built-in operator has an opcode. And I lumped them all together. Some are unary, some down here are binary, index unary, and so forth. And they just keep going, 51, 52. And they're all just lumped in together. Every operator in the whole space of operators has a single unique opcode. And user defines are also one opcode. Well, if it's user index unary op and so forth. Okay, so these are, but we're going to the matrix. So here's the matrix. Wait, hang on. Okay. So this is the scalar data type. This is the vector data type. This is the matrix data type. And oh, by the way, they're the same. And this is an unfortunate feature of C. I had to fool the C compiler to think these are three different types. I'd like to really define one struct and say, there, a matrix is a pointer to this struct, of GRB vector is a pointer to this struct, and so is the scalar there, full stop. But then this generic gets confused. So I had to literally create three structs like this, but I want the contents to be the same. So this is a little unfortunate use of pound include, and I'm not using this in a templatized way. I'm using this in a fake C compiler way. So this then is the content of a GRB matrix. It's the content of a GRB vector. It's the content of a GRB scalar. All right. Different name for actually, this should also say scalar object as well, because they've been added later, and I didn't add this to this just yet. So, so what's in an object? My objects always start with this stuff right here, including the operators, actually. And so I can take any of my objects and look at the first integer, first 64-bit integer is a magic number. And this tells me, because GraphBLAS, I'm supposed to detect if it's an uninitialized object, if it's a freed object, if it's an invalid object, and so forth. And so that's this magic number. And it's just a weird number I stick there for that. And then everything I malloc, totally everything. When I malloc something, I malloc some object, I always somewhere, not with the pointer itself, the pointer is still an 8-bit, I'm sorry, 8-byte, 64-byte, 64-bit pointer. I always store the size of the thing that I malloced when I malloc something. When I free it, I also pass in what I think the size of this thing should be. And so I can keep track of my memory references that way and the sizes of these objects that way. And that's what this is. So this is when I malloc this header, which is, I don't know, about 200, 230, 100 bytes on that order of magnitude. I store that size here. And if it's not initialized, it's 0. 0 is special. 0 says, well, it's not actually malloced. Why would you have a header that's not malloced? Well, if I'm creating a temporary internal matrix, I don't malloc this struct. I can define it on the stack and then just stuck this things in it. And that's what the scalar wrap does. If I have a C scalar, I can slap the struct around it in no memory allocation. So the header side would be 0 if it's actually a static header. So the next thing in here is a pointer to a string, because the user can get this name of a matrix. And then also if there's an error and the error is recorded in an out like GRB MXM and you have a typecast failure because you can't cast double to Gaussian integer or something like that because there's no typecasting to user defined types, the error message gets put into the output object. And so that would go here. And GRB error on a matrix or on a vector will retrieve that string. So I have to have a logging mechanism for logging an error. So these are the basic things, kind of boring things. Now we get into the more interesting things. We have to know the type of the matrix. So yeah, it's just a GRB type. So a arrow type is the GRB type of that object. And I just use the GRB type here. I don't use I do have a type code. I do have an enum that says which built-in is it. So I have like 13 codes, 12 built in, and the 13th is user-defined. But I actually need to know the precise user-defined type. So the only way to do that is the pointer to the actual type itself. So I can get the entire type there. Now we get into the data format, compressed sparse vector. So by vector, what do I mean? If this is by row, and the matrix is 4 by 10, then I'll have 4 vectors of length 10. And I don't store n rows or n calls. I don't know. If I look at my data structure, I do not have a place where I have, this is how many rows this matrix has. I don't have that. It's like, well, I need to know that, right? Well, yes, of course, I need to know that. But I call this number 4 the vector what do I call it? Dimension, which is I don't know, it's a rather unfortunate choice. It's the number of vectors. It's the dimension of, not the length of the vector. This is 10 right here is the vector length. So if I have a matrix that's stored by column, that's 10 by 4, it's the same data structure. These two are the same data structures. I just have a flag that says, well, who are you? And the name is kind of a leftover from when it only had the CSR CSC. It is CSC. This would be true. This would be false. Otherwise, except for that one Boolean, these two are the same, exactly the same data structure. And this is really useful because once I get into my kernels, I'm CSR CSC agnostic. If you see the word agnostic in GraphBLAS in the source code, that means I don't care if it's by row or by column anymore. I pretend it's all by column internally. But if you're adding two matrices together, you're just adding sets of vectors of certain length. I don't care if I'm adding two row by row matrices versus adding two matrices by column. It's the same kernels. I don't care anymore. And if you're doing like A plus B transpose, there's two CSR matrices. Well, then I'm adding this plus this. Now, how did you get this? Is this a matrix stored by column, or is it a CSR matrix that's been transposed with the descriptor? It's the same thing. And so once I get into my kernels, I then ignore this flag. I just say, well, I've got thingies go this way or thingies go that way mathematically, the vectors, which direction they're going. And so if you have four input cases, imagine you have an input matrix that could be by row or by column, and you have a descriptor that says transpose it or not. Well, that's only actually two cases, not four. And I'll collapse those two cases, those four cases down to the two cases right away. Oh, did you drop out? Oh, you're back. Okay. The recording kept going. I think. It still says the meeting is being recorded. Okay. So if I have a 4x10 matrix or a 10x4 matrix like this is what I call these both matrices would be, so far the way I kind of drew them informally is a sparse matrix. It's CSR CSC. So I actually have then a total though of 8 formats. I have, and this is 2 of them. And the formats I have are sparse, hypersparse, bitmap, and full. And all of these are by row or by column. So that's 8 formats. And these formats are fortunate in that they sort of fit in a nice family. They all sort of fit together in a single family. And so sometimes I'll have algorithms that'll operate on multiple formats almost identically. They'll have a little bit of code somewhere that's, oh, it's sparse, I do this, hypersparse, do that, and oh, the rest of the code's all the same. So it's would be a much more breaking change in terms of these 4 families of 4 methods to add a new format that's totally different. Like imagine a more dynamic graph like what David has in Stinger and his, what's the follow-on to Stinger, where every row is a dynamically reallocatable object and blocked or B tree or something. I forget the data structure exactly that he uses, but it's more flexible, row by row or column by column. I could do that, but it would not be in these families of 8. This family of 8 is fortunate and they all kind of look alike.
But is that, so just to break in real quick, is that something you anticipate needing in the future? Like we talked about, you know, databases having like block storage or tree-like storage requirements.
Okay, so you know, it's an opaque thing, but the thing about the GRB matrix I have so far, I have kind of I've hit a spot in between a completely static data structure and a completely dynamic data structure. I've got something in the middle. I've got somewhat dynamic capability, but not fully. But I need it in the future eventually. I'd really like to be able to handle arbitrarily dynamically modifying graphs that are changing wildly, and then you do matrix operation on it, and then you make a little tweak to the graph, and you do another operation on it. I'd like to be able to support that more flexibly with less painful overhead of, oh, you tweak the matrix, well, hang on, I got to rebuild the whole stinking thing. Right. That's what I have to do right now for the sparse and hypersparse cases. So that's unfortunate. I can batch those changes. That's the thing in the middle. It's somewhat dynamic. You can do lots of little changes, and I don't have to touch I don't have to change the data structure as a whole on every little tweak until you want to do something like add 2 matrices, multiply 2 matrices. Well, then hang on, I got to finish the work. So I can batch those changes, but I can't do more than that. Okay.
But you're not precluded from moving that direction if
Well,
necessary.
yeah, it's an opaque data structure. That's the beauty of it. I could, yeah, totally do that. And the API on the outside wouldn't change, except you can give me hints on what format to use. Now, I will choose between these 4 formats. I choose automatically. I don't make this choice automatically. By default, it's by row. Everything is by row. If you make a matrix, I always store it by row. Unless it's a vector, then I'll store it by column. GRB vector, store by column. And I think if you ask for a GRB matrix that's n by 1, I'll store that by column too. I forget. But a vector, certainly, a GRB vector is always stored as a by column format. But no, I could totally in the future change this.
Or add to it, you know.
Add,
Yeah.
obviously. What about delete these?
Yeah.
And
there's a couple interesting papers on banked memory FPGAs that have a format called CISR, CISR.
okay.
That's like a tweak on CSR, but offloads a lot of the positional decoding to be easier in hardware than sort of what you have to do in software. I'll send you a couple links to that paper. I'll be honest with you, like I read the paper and it didn't quite completely make sense to me, but it might make more sense to you.
Yeah. So right now, you know, the one thing that's really costly about this format is I use a lot of 64-bit integers, and that's kind of overkill. And having some sort of compressed data scheme, or at least even smaller integers when I could use them. I don't support that right now. But in the future, yeah, I want to handle more data format, definitely. Cool. More dynamic, more suitable to hardware. You know, there's all sorts of directions that formats can go. But it's no small feat to add a new format, because I have to then make every algorithm work on that format. Every algorithm then has to work on that format.
Yeah. And like you said, something like reduce, maybe that's not such a big deal, but
no.
MXM and yeah.
Exactly. Okay, so I have these primary components of the data structures, these different formats, that PH, IX, and B, or FIBX, PH, BIX. Those are 5 different arrays that I'm going to use for these 4 different formats in various ways. Okay. And so, and in the code, you'll always see things like uppercase followed by a lowercase letter is always a matrix, and that's its component of the matrix. So AP, AI, AX, AH is always abbreviations and point. When I'll pull in the pointer, I'll say that's the AP array. It's A arrow P, and so forth. And you'll see these components down here. So I have these then 5 different arrays: AP, AH, AB, AI, and AX, which will be used for all 4 of these. And this is the FIBX, PHBIX. Okay, and how are they used? Well, but see, some of them don't need, like, for example, bitmap and full don't use P and I, or H, they'll use B and X, or just X or something. So what are these? So let's look at these 8 different formats. So this is so far just comments. So the full matrix, well, then all I have is the numerical array. And the FIBX arrays are all null except for the AX array. And I keep track, not only do I have the number, oh, it's 4 by 10, but what if I had maybe make this 5 by 10. But what if 0, 1, 3, 4, what if it looks like that? Like row 2 is empty. Okay, well, if row 2 is empty in a CSR format, I still have an empty slot for that. I'm going to have a slot for that empty row. So I have a vector dimension, but I also keep track of the number of actual vectors in the data structure, and a full matrix of the same. That's what I've highlighted here. they're the same. And the thing is either stored, so it's a full matrix, it's either stored by a column, by row, depending on this flag. And so this is easy. A column is held in, it's just a full matrix where it's like if the leading dimension though, is the same as the number of the length of the vector. Okay, so this this vector here, are you hearing those beeps, by the way, from my phone or from I'm trying to, my laptop is talking to my phone and I'm getting.
Slightly, just very faintly.
Yeah, let me turn my phone off. I'm sorry. This is
Or you can put
really,
on do not disturb or
I don't know how to do it on my laptop here. I thought I had do not disturb here. Yeah. All right. Okay, there I've got it.
it's barely coming through the audio, so I don't think it'll
Yeah.
affect the movie.
Yeah,
It might
sorry
just
about
distract you though, yeah.
that. Okay, so that's the full data structure, where then the full data structure, say if it's stored by row and it's 5 by 10, it's simple. All I have is the AX array, and it's stored in this, 10 entries of the first row, next 10 entries are the second row, and so forth. Okay. Now, the interesting thing about this data structure, there's no gaps. Like in an LA pack or something, or you might have a matrix that's, it's 5 by 10, but the leading dimension is 12. You've got this then empty space here of 2 entries at the end of every column. I don't support that. I don't do that. As a result, what's interesting about this full matrix, it's actually very similar to a sparse matrix that has every entry present, but you just throw away the integers. Take the integer data structure for a CSR matrix that is completely populated, throw away the integers, well, you have the same data structure, which is really useful. So full just becomes a special case of sparse. And if it's stored by column, well, it's just flipped, there. That's stored by column. And bitmap is sort of an in-between structure. It's just 2 full matrices. One is the numerical values and one is a uint 8. It's not really a bitmap, it's like a bool map where the entry is true or false. And internally though, I got 8 bits I can play with. Sometimes when I need to set certain conditions about the matrix, say as I'm computing on it, like, oh, this is an entry where I've put the mask into the bitmap. I put something other than, I'll put a 2 or a 3 there to denote something different than a 0 or 1. But any matrix that give back to the user, those are back to 0s and 1s. So the bitmap would be 2 of these. 2 of these arrays. One, a numerical array of the given type, and the B array, which is uint 8. And it'd be the same size, 5 by 10. So that would be the bitmap format. And then the integer arrays, P, H, and I, are null. And so the bitmap is 2 arrays. Actually, int 8, not uint 8. Sorry, I have negative numbers there, I guess. And sometimes what I'll do is what I'll do in my internal, and I have macros here to illustrate this. There's no integers in this data structure, but I can always fake them, if you will. Like if I wanted to pretend that this full matrix was a sparse matrix and it has, it'll have an AP array of size 6, because it'll have to have 0, 5, or 0, 10, 20, all the way up to 50 is the last entry. That would be, if I had stored this as a sparse matrix, I'd have an AP array of, say, 5 plus 1. I don't need it, of course, for this format. But if I was stored it in a CSR format, I would have an AP array of size 6. I'd have an AI array of size 50. So but you can compute AP of 1, for example, should be 10. I can compute that. So I'll actually have a macro capital AP of 1, which will give me 10 if I need it. And this is just the row index times the vector length, 10. And the column index, if I want to know what's the column index of that entry, well, it's if it's the 15th entry, this is a mod function with 10. This is like take the AI of 15. What is this? Well, this is take 15, divide it by 10, and take the mod. It's 15 mod 10, which will give me 5. So this is all the integer format of this matrix. If I need it, if I want to pretend this matrix is sparse, I can do that with a computation rather than with a lookup. Now, of course, that's overkill for a full matrix. Why would I do that? Well, if I want to combine algorithms together and have one algorithm that works with an input that's full and one and also sparse at the same time, I can do that. And it just is a one level. It's just a macro that defines that one accessing these arrays are doable. And I'll show that down below. Bitmap is then two dense matrices. That's what this is describing. CSR format is just the conventional CSR, where I will have an AP, an AI, and an AX format. And so this would, for this matrix, this would be a size 6. AI would be a size, well, how many entries you have. And then this just tells you where they start, and then 6th position is equal to E as a placeholder. And then AX is normally the same size as the AI array. So this would be a CSR or CSC format, which I just call sparse. If you say, oh, it's a sparse matrix, well, then it's actually compressed sparse row or compressed sparse column. I just call sparse. All of these matrices, all of these data structures can be ISO valued. So if I want for me, P is if you see the single letter P in my code, it's not a pointer, it's actually an index. It's an index into this. So the Pth entry is at a position AI of P and the value of AX of P. That's if it's not ISO. If it's ISO, this is the same, but this changes. Then all the values are stored there. And so getting the Pth entry of this matrix actually can be done with this with a ternary ISO $0:P like that. So if I have an ISO valued matrix and I want to have the test at the last minute, I do this. Like if it's ISO value, just give me that value right there. And this array becomes size 1 then, because I'm only looking at position 0. Position 0 right there, the size of which then is 1. And otherwise give me the Pth entry in this array. And so this ternary happens at the very last minute. If I have what I call a factory kernel, or a kernel that's built into GraphBLAS that I don't JIT. If I JIT, I know at JIT time, at compile time for the JIT, if it's ISO valued, I'll compile a different kernel for it than if it's not. And so this ternary becomes a compile time turn. It just becomes a 0. It's not ISO, it becomes the number, the expression P that I'm looking for. So in the JIT, I compile away those different tests. So that's sparse, hypersparse. I have some code that are down below in the same file, which explains to you a little bit how I walk through these data structures. And I think it'll hopefully make these data structures more coherent. A hypersparse or doubly compressed matrix is a matrix that looks just the same as this sparse case, but with one extra addition, the H array, which is size 5, which is the number of vectors. See, the P array is equal to the number of vectors plus 1. In a sparse array, the number of vectors, which I stored, this is A n vec. If this is a sparse, a CSR, CSC matrix of this shape with AP is length 6, the number of vectors is the same as the vector dimension. But in a hypersparse matrix, it looks like this. Because I might not, this, I could define this vector dimension now to be 10 to the 30, say. And only 5 of them are present. So now imagine a matrix here that's not 5 by 10, but take the 5 out and put 10 to the 30 there. Make it ginormous. So the matrix is 10 to the 30 by 10 stored by row. Okay, how would I do that? Well, you're looking at the data structure right here. If I have 5, well, actually, I said here I have 4, but let's stick with 5 the way I've drawn it. I've got 5 vectors in this matrix that are present, that have something, potentially something in them. And I have to have their 5 names. Like this is row 1000, this is row 1,000,000, this is row 3,000,000,000, whatever. I'll have 5 non-empty rows, and then the rest of the matrix is the same. So if you think of a hypersparse matrix, all it is CSR, say, it rather than storing the matrix as M by N, let's just use M and N, not number of rows, number of columns. It's M by N, let's say. A hypersparse matrix, I pretend to store it as a CSR matrix that's equal to dimension of the number of non-empty rows by the length of those rows. But then I lose information if I just do that. It's like compactified. Well, I've got to know what those rows are now. I have to store the information. That's the H array. So what I'll have here is like, this is there's 0, 1, 2. I'll have the number K. This is the kth vector. Like there's the kth vector in the matrix is the second, 0, 1, 2 would be the third. So the kth is 2, but I need to know its name, and that name is J. If it's a stored by row. Oh no, sorry. J is a column index. Internally, Internally, I said I pretend all my matrices are stored by column, so that's why I'm using the letter J. J is a column index, so this would be a row index, but if it's CSR, if it's by row, but I call it J instead. Every vector has a name. So if this is the millionth row in the matrix, that name million has to be there as, say, the third vector. So the K is 3, but the name AH of K would be that number J. So if I want to ask what's the kth vector, what is its name? Well, it looks like this. Its name J is equal to AH of K if A is hypersparse. Otherwise, it's the same otherwise. So that's the difference between hypersparse and sparse bitmap or full. So this is the case here for sparse bitmap and full, and this is the case for hypersparse. And again, I can make this a ternary. I can say J equals, are you hyper? Is A hyper? Yes, question mark. I don't think I have an A arrow hyper. I think just if AH is null. Question? K. Otherwise, AH of K. So there's the ternary. Get me the name of the kth vector. Oh, okay. Well, if you have a hypersparse list, you're hypersparse, then give me AH of K. Otherwise, just give me K. That's the name of so to look up for giving the kth vector, give me J. Now there are cases where I need to do the opposite. I want to say, well, given J, what is K? Like if I say, if I have a hypersparse matrix and I want to say, well, give me row 1,000,000. Well, oh, it's a hypersparse. I got to look for it. Maybe with a binary search. I have another data structure for that to make it faster.
And that's the sorting requirement is for quick lookups.
Oh, well, no, it's more than the sorting. I always keep the AH array sorted always. But yeah, that would be like a binary search, but I want something faster than a binary search. And that's what I hash it. I have a hash table. That's what I call a hyperhash. I'll explain that in a minute what I do, but I want to invert this function. I have this list always. If it's hypersparse, you have this H array. If it's not hypersparse, you don't. And that's the determination. Are you hypersparse or not? If that array is present or not. If you're hypersparse, if you're given K, you can quickly look up J, but how would you invert that array? Okay, well, the binary search, like given J, find its position in the hyper list. That could be done with a binary search. Yeah, that's what I used to have only. Now I still can do that if I don't have the hash, but I also create a hash inside the matrix that makes this faster and better on the GPU as well. So that's I call that the hyperhash. So, and I'll before I talk about the hyperhash, I'll jump down to the end of this file, has some sample code that I would use to walk through these different matrices, one row, one vector at a time. But first of all, now the primary matrix content then is the PHBX, PHBIX. So I have the PHBX here. H is for the hypersparse list. P are the pointers for hypersparse and sparse. I is the indices for sparse and hypersparse, not for bitmap and full, and the values, which is then a void pointer because it could be anything. And it's of size equal to the number of entries in the matrix if it's full or sparse or at least that big. But if it's ISO, it's size 1 item. And in the bitmap, though, if it's ISO valued, you still have to have the big bitmap. And this is only for a bitmap case. So this X array is used for all 4 data types. I store an explicit entry of for GRB matrix nvals returns a number. That's the number right there. Because these different formats might have a different way of giving you that nvals. CSR is easy. You just look up the last entry of the P array, and that's the number of values. That would be easy to look up, and that's all I had for a while. But then as I got more formats, I decided I would put this in there as well. And this is then always the case. And if it's full, I might not use this number because it might be too big. Because nvals can exceed 2 to the 64 for a full matrix. I can store a matrix with more values than there are milligrams in the sun for certain cases. I'll explain that how that happens in a minute. So the PHBX then, I have the 5 pointers. I need to know the size of their 5 arrays. That's the P size HBIX, the PHBX size and the PHBX pointers. So the ISO case is really important because unweighted graphs are all over the place in graph algorithms. And so matrices where all the entries that are present have the same value, whether it's 1 or pi or whatever, are really important. And so how do I store that? You saw how I did that here with this AX array just becomes a size 1. And what that means then, if you have a sparse matrix, say an unweighted graph, where all the edges are 1, well, then all I have are these 2 arrays if it's sparse. This array is present, but it's size 1. It shrinks. If you have a bitmap matrix, I have to store a full dense matrix of the bitmap, 1s and 0s, 1s and 0s, and so forth, true and false. So that's a big matrix still. That doesn't shrink if it's ISO valued. But if it's an ISO valued bitmap, X is size 1 entry. Now, what's interesting is a full matrix only has this array. All the other 4 arrays are null. So an ISO full matrix then is no space at all. I just have to know its header, which is about 200 bytes or so, 240 bytes, I think, and 1 pointer to an array of size 1 entry. And that thing can then hold a full matrix of whatever size I like to make it. And the dimension can be up to 2 to the 60 by 2 to the 60. I can create a 2 to the 60 by 2 to the 60 full matrix that's ISO valued in constant order 1 space. But that makes this a little tricky. How many values? GRB matrix nvals of that. I have to return like uint64. I overflow. If you ask how many entries under a 2 to the 60 by 2 to the 60 full matrix of all equal to 1, I have to return infinity. I have to return uint64 because I've overflowed. I have to just give you I've an indicator that says, hey, it's really big, and I can't actually tell you. So
It's gonna be like 2 to the 120, right?
Yeah, exactly.
Yeah.
It's got 2 to the
Yeah.
120 entries in it. And I can't fit that in a 64-bit number. That's not just a cute parlor trick, it's actually useful for things. Because you can do stuff like, you have to be careful. I have to be careful when I touch this full matrix, but I can do things like EY's multiply a 2 to the 60 by 2 to the 60 hypersparse matrix, dot star, EY's multiply with this. Yeah, why not? I can compute that. It's also used for like multiplying matrix times vector. An isofull vector is nice to do a reduction. Like sum up all the entries in every row. Well, that's just A times X, where X is isofull and all equal to 1. And that's what I do actually in GRB matrix reduce to vector. That's all it is. It's a matrix vector multiply. Let me jump over the hyperhash and let me jump down and pending tuples and zombies and sparsity control. Let me jump all the way in shallow and bool content. Oh, there's the is CSC. There's the one bool I've explained. There's other bool inputs as well. ISO I've described, and I have to just keep track of the bool that says, are you ISO valued or not? And if you're ISO valued, the X array becomes size 1 data type, which is then whatever the type size is. It could be 8 bytes if it's double. It could be 16 if it's double complex, and so forth. Okay, now how do you walk through these 4 different formats? The comments below assume we're storing by column just for convenience, agnostically, because all my kernels look like that anyway. And this is just for comments, but I've if-defed it so Vim will describe the color. So it looks like code, but it's not. These are all just comments. But it's handy to have the color so you can see where the codes are, where the comments are. So I have this macro called GBI that says, well, give me AP of I, please. Oh, but what if your bitmap are full? You don't have an AI array. What is your row index entry, please? Well, that's this macro will give it to you. It's just the mod computation. If it's the pth entry, you want to know what's the row index, you just take p mod the vector length, and that's you get the row index, or the row index, because imagine it's stored by column. So it'd be like, it'd be like this. If you're a full matrix then, or bitmap, then I can still look this up. You just wouldn't have this array, but this just means the mod. I might want to say, oh, you're a bitmap. You may want to ask, well, is that entry actually present if it's bitmap, I have a true or false. Otherwise, it's always present because it's not yet a zombie. This is something different. Then if you have a bitmap, then look it up. Otherwise, it's present. And so how do you get the P array? Every matrix has a de facto P array. If you have a P array, you just look it up. That's the start of the kth vector is in this position. But if your bitmap are full, there's the start of the kth vector. It's K times the vector length. What about the hypersparse case? Well, if you have a hyper list, look it up. Otherwise, the name of the jth thing is just, the name of the kth thing is just K. The name of the kth vector is K. So it's by column, the kth vector is column K, just there. Otherwise, you're hypersparse. And so these macros, and how do you get the entry? Oh, if you're ISO valued, there's that ternary. So with these 5 macros, every matrix has all 5 components, effectively. I can pretend. Now, that's could be an expensive, turns out not to be too bad, ternary tests to put all the way down in the innermost gut of the code. So the JIT doesn't do this. But now imagine 4 different codes that just walk through these matrices formats. How do you walk through every vector of a full vector? Well, you get the vector length. What is that? That's the number of entries in every vector. So if it's stored by column, that's the number of rows. And then I want to walk through every column. And the name of the kth column then is just J. So now I'm going to work on the jth column. Where does that jth column start and finish? It starts and finishes right there. It starts at k times the vector length, and it ends at k plus 1 times the vector length. So then walk over those entries in that column, get the row index, which is a mod now, which is overkill, of course. Wouldn't have to write the code this way. This looks weird. Why would you do a mod when you can just go from 0 to the number of the length of the vector, right? Well, I'm trying to make all these 4 formats share the same piece of code. So let me just bear with me here. You see why this should work, right? But you'll see how the other methods look almost the same. And then give me aij. Oh, fine, look it up. There it is. Get ax of p here. Oh, unless it's isovalued, then you already got it. It's just ax of 0. So this is how you walk through a full matrix. Well, how do you walk through a bitmap? Well, it's identical to the code above, absolutely identical with one test. Look up the bitmap. If the bit says it's there, oh, then you have it. Otherwise, it's not present. But you can still walk across this the same way, column by column. Give me the jth column. What's the jth column? Oh, it's the kth vector is the jth column of the matrix. We're still walking through some number of vectors. Each vector has a certain length. The PHI arrays are all null. And for a bitmap or full vector, the number of vectors is the vector dimension. So that's walking through a bitmap. Now, if you look at these 2 pieces of code, you can see right away that I could unify those 2 pieces of code into a single piece of code just with this adding this if. Well, that's what I can do with this macro up above. I can have the same code. What about the sparse case? Well, I don't actually need the vector length anymore because I can just walk through every vector, get the name of its vector, which is just the kth vector is the column J. Now I want to walk through that jth vector. Well, I need to walk through the start to finish. What's the start to finish? Well, it's similar to this right here. I could have written it slightly differently. In fact, why don't I do that? Right? This would make more sense if I wrote it more uniformly. This is just AP of K. And this is just AP. I'm actually going to change my code to make it more clear. AP of K plus 1. And then this loop is the same. I'm not sure why I didn't have this. This is just comments. But now you see a full case versus the sparse case. They look very similar now, don't they? Well, this is bitmap. But this loop right here now is identical to the full loop. Oh, well, except for this. Give me the ith row. Oh, you're sparse. That's what you have to do to get the ith, the row index of aij is given by ai of p. Otherwise, those 2 loops, the full loop and the sparse loop, now look very similar. They differ on how you find the start and end of every vector, and they differ on how you look up the row index. But those macros can hide all that. The hypersparse case looks very similar to the sparse case. So let me make this even more uniform. Let me take these 3 lines of code and put them here instead. There. Now this is slightly different now. So look at the sparse case and compare that with the hypersparse case. They only differ by this. Walk across how many vectors you have. How many vectors do you have? Well, it's something less than the dimension. Oh, this should be vdim, not dim. Walk across your vectors, give me the kth vector. What's the name of you? What's your name, kth vector? Oh, your name is J. Very good. So let's work on vector J. Where do you start and end? The same way as the CSR case. Let's loop across that column. Get out the row index. This is this from here to here. This is the same. The only interesting sparse and hypersparse is this lookup right there. So what that means is I can write a single loop to combine all four formats.
And sorry, where is J being used in these two? I see the assignment.
It's not.
Okay,
But some methods might need that number J.
I got you. Okay.
Yeah, they're not, it's not used in this loop here. Well, neither is AIJ for that matter. Right? It just
Right.
across the matrix. It's not doing anything with them.
I got you. Okay.
But at this point in the code, you have three things. So you know the row entry, the row index, you know the column index, and you know the value.
And then you'll use it for some work.
Something. Yeah.
Yeah, this is just, I see.
The work being done.
Yeah.
Okay. But I can do this then for all four formats. I get the vector length. I walk through all my vectors. I want to know the name of my kth vector. Well, for sparse, bitmap, and full, it's just K. But for hypersparse, it's H of K. Same one line of code that does all four cases. And I want to know where does the kth vector start? Where does the kth vector finish? Well, there's a macro that can collapse those cases down to a single expression, the GBP vector, the macro, which was defined up above. If you have a P array, you're sparse or hypersparse. So look it up. It's AP of K. But if you don't, if you're bitmap in full, then you have to do the multiply to know where does the vector start. It's just the kth vector starts at K times the vector length. So that allows me to pretend I have a P array for when you're bitmap in full, this works. So this will work for any format then. Then go from the start to the end of this vector. And, oh, well, you might be bitmap, so check it. Okay, well, if you're not bitmap, the B array, the little B array, AB, is null. And so this becomes if not one, continue. So if zero, continue. So literally it'll become a compile time away. It'll never be true. Get the row index. Well, there you go. GBI. If you have an I array, you're sparse or hypersparse, then look it up. If you don't have it, then just compute it with a mod. So bitmap in full, again, would be on one side, and sparse hypersparse would be on the other side. And so that's one piece of code that can walk through all formats and do stuff. Like at this point, I have an entry, row I, column J, value is AIJ. There's some interesting things to observe about this loop. First of all, this is a single-threaded loop. Okay, parallelizing this is another story. And it can be very different if it's sparse or hypersparse versus bitmap and full. I can parallelize it differently, like chop it up into different tasks and do stuff. Okay, so there the code might look very different, totally different code base. I might have a kernel that walks across the sparse and hypersparse, another kernel that walks across bitmap and full that are totally different because the slicing that up, and I use the word slice in a very special way. Slice is the word I use. I have a folder called slice. This is how I take a matrix and chop it up into pieces to do parallel stuff on. I call it slicing the matrix, and I have different ways of slicing it. If I slice the matrix, I might slice a sparse matrix different than I'll slice a full matrix. The slicing methods are very simple for the full case. So the parallel methods will bifurcate and do two different kernels, but just it's useful sometimes just to be able to do this kind of loop. The other thing is this observation here about the bitmap case. In some sense, sparse, hypersparse, and full all live in one family, and bitmap is over here. The reason being is that if you consider a matrix with no zombies and no pending updates, which is I haven't talked to you about, in some sense, sparse and full are the same data structure because all the entries that are present are just stuck together in one array from the first entry to the last entry that's present. The AX array. There's no gaps, there's no holes in the X array. In bitmap, that's not the case. The bitmap, this test can fire and say it's not there, jump over it. And so reduce a matrix to scalar, you could imagine then, if the monoid you're using doesn't care about what the row or column index is, well, then actually hypersparse, sparse, and full are all the same algorithm. Just iterate across all the entries of the matrix. And you don't need to know the row or column index. Oh, bitmap, that's different. I got to jump over stuff. But sparse, hypersparse, and full, I can actually have one algorithm that does the same, that works on all three of those formats, and it's not any different. So in some sense, sparse, hypersparse, and full live on one side of camp, and bitmap's over here. It's very different. Other times I'll have the camps where sparse and hypersparse live here, and bitmap and full live here. Those are different because of where things start and finish. And how you divide up, how you slice the matrix is very different. If you have a AP array, how you subdivide the matrix is very different than when you don't. So bitmap and full are sometimes treated together, and sparse and hypersparse are treated together. And sorry, I've got bubbles coming up on my screen now.
Yeah, I wonder if I can turn that off.
I hate that. Those are so silly. Okay, so those are the four different formats. And in this example, I've said, oh, they're all double precision, whatever. They could be, of course, any data type. And then are these held by row or held by column? Well, that's, and again, this is just an internal data structure. So I have this bool. I should rename it. Like but I've just left it alone. It's is CSE. That means it used to be only had one format, sparse, and it was either CSR or CSE. This really means it should be like by column now. I could rename this variable if you're stored this way or you're stored that way. And all four formats go either direction. Okay, so that's the basic four plus ISO plus by row or by column. Does anything there, do you have any questions so far? Other questions?
No, it's making sense. Yeah.
Well,
It's good to, it's nice to walk through it top to
yeah,
bottom.
I got to walk through it methodically because I'm going to throw some loops at it, throw some twists at it. Okay. So that's and this now describes, all the details like, oh, you're sparse. Okay. Column J is held in two parts, row indices here, numerical, and so forth. So we have all that. Now, if you ask a matrix, you can see, well, GRB matrix n rows. It's a ternary because I don't store the number of rows or the number of columns in the matrix. I have to say, oh, if it's stored by column, then the number of rows is equal to the vector length. So I return that as the answer. And if it's stored by row, it's the vector dimension. That's the number of rows. So it's a very last minute thing. The data structure is, in a sense, is agnostic to by row or by column, except for that bool. And that's useful because then I can, once a matrix is inside GraphBLAS and I'm working on it, I don't look at is CSE or is CSR. I've already taken the descriptor and done this exclusive OR thing, collapsed the four cases down to two. So what is this? This is a CSC matrix that's been a matrix held by column that's been transposed by the descriptor. And this is also a CSR matrix, a matrix stored by row that's not been transposed by the descriptor. It's the same thing. And I can ignore that Boolean flag. And then when I pass this to my kernel, that's what I'm seeing. And likewise. So So that's an important agnostic kind of kernel. I can ignore those cases when I make sure I just am doing the right thing. Okay. Then the other thing, what other things do I have? Now I add some extra twists to this. Okay, because if I stopped right here, bitmap in full, I can very easily change any value, order constant time update, insert deletions is easy. Well, not for full. I can't delete an entry if it's full. So it doesn't work. Delete an entry like to make it not present. One entry is not present. I can't store it as a full format. I have to convert it to bitmap. But a bitmap is easy. Just turn the flag, right? Look it up, just change it. It's easy. It's really hard to delete one entry of a CSR or a CSC matrix. Sparse or hypersparse, delete one entry. Ooh, that's ridiculous. You got to shift every other entry over. That's expensive. I didn't want to do that. So I had this notion of zombies. Let's see, I've talked about everything. I've talked about most of these, but not quite all of these. I've talked about the vector length and the vector dimension. This is a fundamental property of the matrix that then when you say GRB matrix new, those things are fixed. They're not going to change. But this can change depending on the format. It's the size of those P and H arrays. Actually, P is that plus one, which could be the vector dimension or the vector dimension plus one, unless you're hypersparse, then it's the number of vectors that are present, which is this number of non-empty vectors. And this, though, is that are stored, like the H array is of this size, but actually some of them could actually be empty. So, and I may need to know that. In other words, I could have, in this example, I could have an empty row in the hypersparse format, but I actually store it there, but it's actually empty. I don't usually do that, but I might have that occasionally, that I then have to prune it out. So the number of actual non-empty vectors is smaller than the number of vectors, and it may not be known. I may delay that computation for later. And if it's delayed, if I don't know it, it's set to -1. So there's already some pending work there. And this number here might not yet be known, and I might not care to know it, so I don't compute it. But it's pending work. But I have more pending work. And the other important pending work is the first one is important, and this is the zombie. What's a zombie? If I have a bitmap of full matrix, never have zombies. A full can't have entries that are not present. The zombie is an entry that's not present. It's been deleted, but it's not been removed from the data structure yet. Well, bitmap doesn't need such a thing. I can just set it easily to just delete it. Sparse or hypersparse, it's different. So what I do to tag an entry for future deletion, I take its row index, which imagine I'm storing everything by column. Its row index is in this I array. If it's a 3 and I want to mark it for a deletion, I don't put a 3 up. Well, I'm going to change this. Let's say I put a -3 there. -3 means, yeah, you were row 3, but you've been deleted because it's a negative. Okay. It's like a tombstone. Your name is 3, but you're dead. That's a zombie. So you're still in the land of the living, but you're dead. That's a zombie. And so if you grep the word zombie, you'll find it, everywhere. If I use something more generic like that, it'd be harder to find. But zombie then is a very special name. The downside, I can't just negate it though, because 0 is a row index and -0 is just 0. So I have to use a function called flip, and I have a folder called zombie. No, where do I have a folder called flip. Where is it? I thought I had. No. Oh, there it is. It's part of my math. folder. Okay, so this is the zombie handling functions. They're just macros. They could be static inlines, but I just made them macros because they're so simple. Flip is a function that it's its own inverse. Flip is x. Flip of x is just x. And it's minus I minus 2. So it's like a negation about minus 1. Like a negate about minus 1. So the minus 1 inverts to itself. 0 goes to minus 2. Minus 2 goes to 0. And 1, if I flip it, I get minus 3. If I flip it again, take the absolute value of flip, you will. Flip it again, it goes to this. So this unflip macro is like an absolute value. And this potentially unflips a row index and gets it. So it's bitmapper full. It's looks up the index and then flips it, unflips it if need be, and gets its name if it was dead. So I have these various macros that handle these different zombie cases. Are you a zombie? Are you flipped is the same thing. Are you not flipped? That means you're positive. Take the absolute value, get your name whether you're dead or alive. And so zombies are useful because it's a pending deletion. Okay, I can tag an entry for deletion, but I don't just say tag it by giving every deleted name -1. The reason I don't want to do that is because it becomes very hard to do a binary search. Like if I have a column and I want to find a given entry, I'd like to do binary search. What if I come across a -1? All the zombies are dead and they're -1. Well, then where do I go? Oh, binary search doesn't know where to go because it's no longer a sorted array. But with this flip operator, I have a tombstone. I can still do binary search. If I do see a negative number, I have to actually get its name to know where it is in the order that I can do the binary search on, but I can still do binary search with across the dead. So if I'm walking through a cemetery and there's live people in the cemetery and tombstones, I can still do binary search on that list. So that's why zombies are really useful. If I have a bunch of deletions happening all at the same time, I'll do all the deletions and I may then postpone the actual construction of the actual compacted matrix with the deletions been applied. I can do that later. So there's a GRB remove element method in particular. If it's sparse, it just sets it as a zombie and you're done. It's a constant work, almost constant. It's a binary search to find the entry, perhaps, but just to kill one entry and make it a zombie, unless it's already a zombie, in which case there's nothing to do. I also use zombies a lot in my assign and subassign methods, where I'm assigning one matrix into another. All my kernels for that, I have 40 of them, ridiculous. Almost all of them create zombies or have pending, the opposite, which is pending tuple, I call it. So zombies happen in potentially any method can have a zombie because the final phase of every algorithm is to pump the computed result through the mask and accumulator phase. I sometimes will use my assign kernels to do that because if it's a very big matrix and the mask is very sparse, you have a tiny change to a big matrix, I handle that very efficiently with my assign methods, and they just tag a few zombies. So zombies are really useful for delaying this work. Some of my algorithms are zombie tolerant on input. Some algorithms construct output with zombies, but so it's like somebody else delete them later. The next algorithm may take as input a matrix. It might say, oh, look, there's zombies here. Okay, I'll handle that especially, maybe a special case, or maybe a method that skips over the zombies if it sees them and so forth. That can be done in a lot of, I could do it in more algorithms. I do it only in a few. I only have a few algorithms that are tolerant of zombies. But like assign, set element, delete element, that sort of thing. extract element, get a single entry out of a matrix, I don't have to kill all the zombies to get you that number. So it's zombie tolerant. So I can then postpone the deletions of zombies, which is expensive. Just in the movies, like if you have one zombie coming after you, that's really nasty. If you have a million, it's really easy because it's the same work to kill a million zombies versus killing one. It's the stormtrooper effect, right? Same thing. One stormtrooper is really dangerous. 100, it's like no big deal, no worse than one.
Right.
The same thing with zombies. Killing one versus killing a billion is the same work. So many of my algorithms will have you'll start off on looking at their input matrices and asking, is there pending work in this matrix that I cannot tolerate? If so, do a GRB matrix weight on that input. So finish the work. Like if I have an algorithm that's zombie intolerant, then if on input I have zombies, kill the zombies, do a weight. Well, that's expensive, but I got to do it right then. So I'll have a lot of conditional weights, like on input, weight if the matrix has zombies and pending tuples, but not if it's jumbled or other kinds of pending work. Zombies are just one of them. Well, the second one, because I also have how many non-empty vectors do you have matrix? I may need to know that. And if it's -1, I may need to compute it. So I'll compute it.
Is that the sort of worst case on that is like scanning the whole object and rebuilding it?
Yeah, that's the worst case. Like if I've got to kill the zombies, I've got to rebuild the input matrix entirely. Yeah, you got to just it's order number of entries work. It's costly.
And that's not is that in place, or do you have to like remalloc?
I think the killing of the zombies if I recall, no, I don't remalloc it. I don't think. I think I just do it in place.
Because it seems like zombies imply
Hang
the
on.
output.
Yeah, no, I don't do it in place because I have to do it in parallel.
Oh, okay, yeah, yeah.
And doing it in place if it's parallel is really hard.
And so zombies imply that there's entries that are going to be removed, and pending work implies there's entries that are going to be added.
But no, pending work is sort of a catch-all phrase for all pending operations I have to do, including zombies.
Okay.
Okay. And how many vectors are non-empty in this matrix, please? I may need to know that. That's already two kinds of pending work, but there's more.
Got it.
The other thing is a pending tuple, and that's this data structure. It's an entirely its own data structure. What is a pending tuple? I call them in the data structure, I call them a pending tuple. I really should have called it, a pending update, a pending insert.
Mhm.
This is an insert that has not yet been done into the CSR matrix. So between the two, a zombie is a pending deletion, and there goes the.
No, I'm gonna try and turn that off.
Yeah, so zombie is a pending deletion. A pending tuple is a pending insertion into the matrix.
Or update.
No,
Oh, that's different. Okay.
no, because a pending tuple, if I look at all the pending tuples, they're disjoint in their pattern from entries that are actually already in the matrix form.
I see.
So a pending update is not put in here.
You just do it right. You just do it in place. Yeah.
Right. I never have a pending tuple that's pending update to be updated to, it's already there. I'll just put it there. Like if I have to add it or have to assign it, I do that. I never postpone that. I postpone the insertion of a new entry that's not already there.
Got it.
So there's some algorithms that can exploit that fact that could be tolerant of pending tuples, but actually don't. Like imagine reduction to scalar. Like you could just say, well, fine, add up all the things that are there, skip over the zombies, then add up all the pending tuples, and then you're done. You got the number. I could do that, but I don't. The reason I don't is because this data structure of pending tuples has to also contain an operator that's a pending operator that says, what if I have duplicate updates, duplicate tuples to the same place? I have to have an operator that collapses them into one. If that operator happens to be plus and you're doing a sum reduction, well then, yeah, I could just add them in any order. But what if the operators don't match? Then I can't do that. So the pending object, what is it? It's an entry. So the pending tuple is an entry that I tried to insert into the matrix and I couldn't because it's not there. Like stick this number aij into the matrix. Oops, it's not there already. So what do I do? Well, I'll do it later, maybe. And that's what if I want to do it later, I'll put it in the list of pending tuples. The list of pending tuples is a list of inserts that are pending into the matrix for only for the sparse or CSR, sparse or hypersparse case. And in some sense, they're unordered, but there is an ordering of a kind. They're unordered in terms of the row or column index. You can't assert anything about it. Go down the rows. They're literally just like row index, column index value. Okay, tuples as in extract tuples, right? The list is a list of tuples. Build takes as input those same three arrays. Okay. And in fact, to do the insertions, all I do is do a GRB matrix build on that list of tuples there. And then I do an add and I'm done. A sparse matrix add. Okay, with a special property that I'm adding two matrices with a disjoint pattern. Otherwise, that's how I kill pending tuples, pending insertions. But just as GRB matrix build in the spec has an operator to handle duplicates, so I have an operator here that tells me how do I collapse two entries, two updates to the same place. What do you mean? Do you mean like if these are assignments, just we'll take the second one? Well, what if it's assigned through an accumulator? Well, then the accumulator is the pending tuple, a pending operator for the tuples. What if the pending operator changes? Imagine you're doing assignments into a matrix and you've got a list of pending tuples and that pending operator is max. And what if you then do a min and you do an insert with a tuple with a min? Well, then there's two operators. I don't handle that. Then I collapse it. So if you do another insert with a pending tuple and want to put it there, well, the operator has to match. Otherwise, it gets too complicated. So this is useful for, again, delaying, it's batching my inserts into the matrix. So this gives me my limited dynamic capability of the matrix. You can do lots of little changes as long as you don't like look at the matrix and do anything hefty to it. Just do bunches, more inserts, more inserts, more inserts, more deletions, great. You can do inserts and deletes, great. And then, okay, now do something real like add or multiply or something else. Whoops, I got to kill them all. Kill the zombies, assemble all the pending tuples. Okay. I have to keep, so the pending object might have an operator. It might have no operator, in which case it's take the last one living. Like if you have two updates to the same place, take the second one in the list. So I keep it ordered in that sense. If you're inserting one at a time, that in that order is important in the order of insertion. The last one lives and overwrites the first one. There might be an accumulator operator. Then that would become the pending operator that's used to sum up the entries. I may need to do typecasting. So I actually store through the operator or through the cast. So if I have if I double matrix and the pending tuples are float, I store them as float, because I have to go through the operator to get to the matrix. And so I store them in the original type that they're in. So if the type changes of the pending updates, I have to change the pending, I have to collapse them as well. I can't change the type, can't change the operator. And I don't change the order, just keep pending on the end. So the pending object, where do I define the pending object? I think I define it in the same file here. What time is it? 12:40. Oh, let me write this because I just made some changes. 12:43. Okay. Opaque. I have this other object. Yeah, here's my pending structure. There's a whole bunch of stuff here. This is an object called the pending object. That's the size of the object. It's how many to add, how big are the three arrays? Do they appear in order? I have the row indices and their size, I'm sorry, the column indices, and then the values, the type of their values, the size of the type, just so I don't like, oops, you just freed the type on me, that's bad. So I don't have to look up that to free the thing. And what is the operator that I'm going to use to assemble these pending tuples? And so what I'm able to do then, once I have this list, if I want to combine all these tuples together to add into my matrix and to handle the duplicates, the first thing I do is just do a GRB matrix build. That's what takes these tuples, collapses them down into a matrix. And GRB matrix build takes an operator called dupe that says, how do you fold them together? Now in GraphBLAS, the GraphBLAS API, not SuiteSparse GraphBLAS, the GraphBLAS API for the GRB matrix build function says that the dupe operator must be associative because you can have the operators being assembled in any order. And the order of the inputs don't matter. And the dupe operator couldn't be like f of xy is y, like second. But I allow for that. So I allow my dupe operator for GRB matrix build to be non-associative because I want to use things like the first or second operator. Second means if you see two duplicates, take the last one in the list. That's useful if I'm doing a bunch of assignments, the pending operator is second. So if I have a bunch of updates, update, take the second one. Oh, but if it's 3, take the last one.
Because that was the like the in time order, that was the last update.
Insertion time, right?
Yeah.
Take the last one standing. And so that operator does not have to be associative in my GRB matrix build. The reason is because so then I can use GRB matrix build to collapse this. Not so much that I can provide that feature to the end user, although that's also useful. Like this is a common thing in a lot of other sparse matrix data packages. Here's a tuple format, coordinate format, row, column, value, row, column, value, row, column, value. What if you have a duplicate? Oh, take the last one in the list. That's your result. That's a common, take that value. Don't take the sum, don't take the max, take the last one. Well, that's like a dupe operator being second. If you apply the dupe operator incrementally, you'll take second will then take the last one living. First will take the first one and ignore the remainder. So I allow those as dupe operators to my build function then to support that behavior. And that behavior is very common anyway in building a CSR matrix from coordinate. If you see duplicates, take the last one living or take the first one. That's a common, and I need that also here to collapse these pending tuples into a GRB matrix. Once I then have the GRB matrix, I can use my EY's add to add it to the original matrix, and I have my inserted tuples in my output, which is then an out of place algorithm. But then I don't have to write another algorithm for assembling my tuples. I just use add.
Mm-hmm.
With no operator actually, because they're disjoint. The add function, sparse add, uses an operator to say, well, if you're adding to, A11 plus B11, you have to use the op. Well, they're disjoint, special case. There's no operator to my add method. So that's how I handle pending tuples with this pending data structure. And some algorithms never produce these, like matrix multiply. It doesn't produce, well, no, it can produce zombies, but it never produces pending tuples. There are matrix multiply methods that can produce zombies. Not too many of them. I think just, well, 2 of them. My dot product methods. If you think, suppose I decide that I'm going to use a dot product method for matrix multiply. Maybe you've got this matrix stored by row, this matrix stored by column, and the final matrix, this might be 10 rows, and the length of this vectors are 1 billion. So 10 by billion times billion by 10. Well, that's just 100 dot products, and it's already in this format. Just do the 100 dot products. That's a lot faster, simpler than transposing things or doing whatever. So just do 100 dot products. Some of them might be empty. So fine, I allocate myself a 10 by 10 sparse, matrix as the output, or maybe bitmap even is what I would do. But some of those might be zombies. Actually, that would become a bitmap matrix, that example. But another case where the case where I actually produce zombies, not just bitmap is easy. If the output is bitmap, if it's not there, the bitmap says false. That's easy. That's not a zombie because there's no pending work to delete that entry. You can't delete it. But a zombie is for sparse or hypersparse. Now, I have a method that does matrix multiply that produces a sparse matrix, but possibly with zombies. And that's the masked dot product, where you have perhaps a large square matrix, maybe, times a large square matrix goes this direction. Multiply them, but pump it through a mask. Then one way of doing that is just by iterating over every entry of the mask, and each entry do a dot product of two sparse vectors. It's a set intersection then of those vectors. And that can be very efficient, but it can also produce an output that says, ooh, those two vectors are disjoint. The output is, I can't put a 0 there because there's no such thing. 0 is not special. I have to put an empty. I have to say it's not there. So my output then is the same pattern as the mask, but I may have to actually stick a zombie to indicate, oh, well, this one didn't actually get in there in the output. So I'll stick in a zombie on the output and I'll kill it later if I need to. So zombies can be produced by many algorithms. Pending tuples there are fewer methods that produce them. The assign methods can all produce tuples, pending insertions. Like set element, one element. Set one element. Okay, what do I got to do? Well, if I try to set it, if I find it's there, I just change its value. Great. I might find it's there, but it's dead. It's a zombie. Oh, it comes back to life again. I dig it out of the grave. You're no longer a zombie because you've been set. It's not a pending update. So what this means is that zombies and pending tuples are disjoint. There's never a pending tuple into a zombie, ever. There's never a pending tuple into an entry that's there, that's live. Never, ever. So the zombies, the live entries, the zombies, and the pending tuples are all disjoint from one another in any given matrix in terms of their sparsity pattern. Of course, this is just for sparse or hypersparse. Bitmap and fill never have zombies or pending tuples. Okay, so that is the pending tuple structure. So this gives me a limited form of dynamic graph capability. It's limited in the sense that you can toss a lot of updates and deletions and insert chains of values up to into this big morass of this data structure. And that's great until you need to do something hefty like matrix multiply, matrix add, transpose, algorithms which are not tolerant of zombies or not tolerant of pending tuples, then have to finish the work as a batch. So it's useful for incrementally making a new matrix or incrementally changing a matrix until you then need to do something significant with it.
Yeah, I guess we've seen like a worst case of that with Louvain, where every loop tries to do an update.
Yeah, right.
On a row,
right.
Or it tries to remove a row.
Yeah.
And then do a multiply, and then put that row back and remove another row. Yeah.
It's nasty. That's a worst
Right.
case for me, unfortunately. Now, if I were able to support a much more dynamic graph data structure like Stinger does, then that would be an issue. Now, it would have the downside, though, of losing performance over a method that, like a CSR matrix is so nicely compact, it's all in order. Operating on that is faster than operating on a data structure. If you're not changing the matrix, a dynamic data structure will be slower.
Right, because you're doing a lot more dereferencing, right?
You're wandering all over the place. You're like, oh, this row is over here and that row is over there, and your memory traffic is worse. And so that is less than desirable. So my performance versus dynamic behavior trade-off is more towards performance for static objects versus being able to do wildly dynamic data structures. But I got a little bit of dynamic behavior in the middle, pending updates and zombies. And one more I haven't shown you, one more pending amount of work, which is very useful to have. And that's just a single bool that tells me about it. And that's inside the matrix. And that's this. Are you jumbled?
The jumbling, yeah.
The jumbling. And I intentionally did not call this unordered. I didn't call this unsorted, because you grep for the quote, grep for the word sort or unsorted. It's like, well, where is, this could be some action you're taking. A sort is a verb and a noun and an adjective, whatever, sorted, unsorted. Okay, so I wanted to have a special name for this specific property. So here, the property is a property of sparse and hypersparse. Never, bitmap and full matrices are never jumbled. But a jumbled sparse or hypersparse matrix is one in which you look at a particular row of your matrix, say, and as you traverse that row, do you see the column indices in ascending order? I never have duplicates, by the way. You'll never see, oh, there's column 10, and oop, there's column 10. No, you won't see that. There's never duplicates, ever. But if it's unjumbled, then they're in ascending order in any given row or a column. It's stored by column. All the row indices are in ascending order. And that's useful to know, because if that's true, I can do things like binary search on a column or a row. If it's stored by row, I can do binary searches. In the hypersparse, this does not apply, by the way. The hypersparse list is always kept unjumbled. I never keep that out of order. That's too hard. Otherwise, I couldn't look it up very easily, right? It'd be very difficult. But the row indices of a matrix stored by column could be out of order. And if that is the case, then if they're out of order, then I set this flag. And if they're in order, then this is false. Jumbled is false. If they're out of order, jumbled is true. Actually, if jumbled is true, it may actually be in order, but I don't know that.
Right.
So where is this useful? Well, if some algorithms like, say, EY's add, or EY's multiply or transpose and so forth, some transposes don't. Many of my algorithms, I would say most of my algorithms, produce an output that is naturally unjumbled. It naturally produces the output in ascending order of indices. Some algorithms naturally do not. Like the Saxby style, Gustafson style matrix multiply sometimes can produce, because you're doing set unions of sets, and you just tack on the appending to the set. It's out of order. Okay. So if that's the case, then an algorithm would set that flag to say, hey, here's the output, but by the way, be careful, the indices are jumbled. Now, this is very useful because there's a lot of algorithms I have that some algorithms can produce them jumbled. But many algorithms don't care if their inputs are jumbled. They work just fine without any change to the code at all. The algorithm doesn't change if it's jumbled or not. They're agnostic. Fine, whatever. So on input, their check of the input matrix there's this pending conditions like, do you have zombies? Kill them. Do you have pending tuples? Kill them. Are you jumbled? Nah, whatever. Just leave it. You see. So I'll wait if it's maybe zombies or pending tuples, but I won't wait on the matrix. Wait means finish everything. The matrix has to be read-only at this point. So finish it, do all the work, kill the zombies, kill the pending tuples, unjumble them, then go on. So So if there's zombies and I have to wait for zombies, I may be jumble tolerant, but I'll get a unjumbled matrix because wait means finish everything, not just one thing. But an algorithm may not have to wait on the matrix and finish all the work if it only pending work is the fact that it's jumbled and I'm jumble tolerant, so fine. And so the input guard to all my algorithms has this check, and the input guard is different depending on the behavior, the characteristics of that algorithm for its inputs. If its inputs can tolerate, if they can tolerate zombies on inputs, they don't wait if there's zombies. They wait if there's pending tuples, maybe they wait if there's jumbling, but they don't wait for zombies. If it's jumbled, that's it, fine, don't wait, depending. Some algorithms are going to do binary search on their indices. And so, whoa, it's jumbled, finish it, don't jumble it. Some, like the breadth first search case, has this vector that's building. And there's there's the frontier, right? Every frontier is its own, a new vector, sparse vector. That comes from a vector, the thing you were showing on the slide, the vector matrix multiply. The push method that I have is doing a set union, and it naturally produces an output that's jumbled. Well, fortunately, that vector is only used a little bit of time. It's used as input for a few other operations, and then it's thrown away for the next frontier. All of those algorithms that read that frontier vector are jumble tolerant. So that vector goes as input to a couple other methods, and then finally it's deleted or overwritten, which is the same thing. And so
I guess that's the benefit of the any operator too, right? It doesn't matter.
yes,
There's like there's a benign race in there.
Right. If I don't care what order, and then I don't care what order I get, or if I do a reduction, I want to find any entry and I just take the first one. Like, what is it? If it's jumbled, well, I get the first one. I don't care.
Doesn't matter, yeah.
It doesn't matter. So if I have an algorithm that's producing a jumbled output, and I don't ever have to wait on it because nobody cares on input with that result, and then I delete that vector, delete that matrix, I never sorted it. And I saved all that time. I never had to compute that answer. I never had to sort all the indices. Because algorithms that want to naturally produce a jumbled output, if I can tell my method, hey, this, yes, I know you'd like to produce the output that's jumbled. Just sort it as you go, please, because I'm going to need it sorted. And the algorithm has to do more work. And if I don't have to do that work, it's faster.
Mm-hmm.
And so then I just set the flag to say, this output might be jumbled. It may actually be, because I may have computed a diagonal matrix and didn't know it. There's only one entry in every row or every column, and it's going to be it's going to be not jumbled. But I'll set the flag anyway if I didn't take special care to sort it vector as I produced it.
And is this a good stopping point?
I think so.
I know we're hitting 11, yeah, or
my time, yeah.
1 o'clock your time, yeah.
Let me. That's all the pending work. Let me just do a highlight of the rest of the stuff that's pending. Oh, there's more. Yeah. So what's left to talk about? We'll just make a list of what's left. The hyper hash. This is a hash.
Yeah, and I haven't seen this before, so this will be interesting for the next.
This is all new.
The next
have
overview
of this hyper list. Okay. And it's super simple. It's a matrix.
All right.
Yeah, it's really wild. My hash buckets are just a matrix. Single matrix is all the hash buckets. Every row is a hash bucket. There's number of zombies I have, sparsity control. I have to control conversions of a matrix between these 4 formats. That's control parameters. How do I know how do I decide when to convert a matrix from format to format as its entries change? I have that. And I have the other notion I have is shallow versus static. Okay. These 5 arrays, the Fibix arrays, might not be owned by this matrix. It might be owned by another matrix, in which case these arrays could be shallow, I call them. Now, I never give this back to the end user. These are all temporary internal matrices. That these objects can be shallow. The header, this might be a temporary matrix, and it's only going to live and die within this method. So the header might just be a static struct that I just then populate. I don't have to malloc the struct header, in which case then I set this to be true. So in the ISO case I have, and that's it. That's my entire format. So there's other things we haven't talked about, the shallow idea, the static header, and the hyperhash is the big thing, and these controls. Those are the things that are left. Yeah. So let's stop there, and maybe next time we'll pick up with the hyperhash, which
Sounds
is
good.
it's a data structure of a hypersparse matrix that makes it fast to look up invert that list, like J, if I have J, give me K, that's the inverse of AH. That's done by the hyperhash. Not all algorithms need or care. So the construction of the hyperhash is pending work for a hypersparse matrix. You can have a hypersparse matrix that doesn't have it yet, because the next algorithm says, I don't care, I'm not going to use it. The ones that need it, build it. And if the ones that don't need it say, I don't care, I'm not going to look at it. And if it's not done, don't build it. So it is also a pending work, the construction of this matrix. Constructed when needed, basically. Okay, so that's the data structure. And I just did a few little comment changes. I'll put in the next version. And yeah, we can stop here.
Cool. All right, well, I'll stop the recording. Do you want to stop?